So we see that light is very important to us. Uh, you remember the experiment that Isaac Newton did with light, in which he put white light through a prism, spread out into all these different colors. So turns out that each of these different colors is a little bit different wavelength of light. So the most bent light, the deep, deep purple, deep violet, that's about 400 nanometers. A nanometer is 1/1000th of a meter. 700 nanometers is the longest wavelength you can see. So that's 400 to 700 nanometers is the range of wavelength that you see. So 700 nanometers is a really, really deep red color. So in that range, you see this. Now, interesting enough, you see 500 nanometers is near the middle of the spectrum. That's kind of a yellowish green color. And so that yellow-green color is about 500 nanometers. So the way your eye works, you see just as many colors between 400 and 500 as you do between 500 and 700. So that's just the way your eye works. It's sort of a logarithmic response. And so that yellow-green color is right in the center of the visual spectrum. And it makes because it's right in the center of the spectrum, it's what your eye's more or less most sensitive to. And that's the range of wavelengths that the visual light is. The different wavelengths have different energies. So red light has less energy than blue or violet light. And that turns out to be important too, because that's why the red light doesn't mess with your dark adaptation as much as the other colors do in terms of exposure at night. So now the interesting thing here is that they did not know about the wavelength of light at first, because remember, it was not until the 1800s that James Clerk Maxwell discovered that light was waves. So they were still thinking about light being particles when Newton was studying it. William Herschel, remember William Herschel, he discovered the planet George, wanted to study other aspects of astronomy, and one of the things he did was study light. And so he got the idea from Newton that light was really made up of all these different colors. So he got to wondering, we know that if you sit out in the sun, it warms you. Do all the colors warm you equally? And so he did an experiment. He took a thermometer, and he set his thermometer down and set it in one of the colors and saw how warm the thermometer get. He moved his thermometer around, and as he was moving it around, he was noticing that it was, not equally heating. Okay, now he didn't know why. It turns out that the material that made the thermometer just absorbed the light energy differently. When he was done, he set it down over here, and he set it down there, and it was beyond the edge of the spectrum. Okay, it was in beyond the red. Now there was no light there, but he was writing down all his observations, and he noticed the thermometer was still getting warm. And he realized that there was light there, just light that he could not see. So it was less bent than red, and so it was called infrared. So there's actually light there that you can't see. Now, remember, William Herschel did not start off as a scientist, and so what happened was he kind of missed out really on a fantastic scientific opportunity, and that was to put the thermometer at the other end of the spectrum and see what happened. And it turned out different scientists did that and discovered there's light that's more bent than violet. So more than violet we call ultraviolet. And so that ultraviolet was what was beyond the violet. Now, it turns out, if you remember, the longer wavelengths have lower energy, so the infrared has less energy than visual light. The ultraviolet light has more energy than visual light. Now, you see light in the range of between 400 and 700 nanometers. Not every creature on Earth has that same dynamic range that you do. So, for example, a lot of insects and some migratory birds see into the near ultraviolet. Now, that's useful evolutionary-wise because that means they can navigate by the sun on cloudy days. So even when it's cloudy, then if the sun's up, then they can see through the clouds and see where the sun is. But they often lose something, so they lose these wavelengths up here. So like a wasp can't see red light. So if you've got wasp nests or hornets nests around the house, then if you approach them at night with a red light, they can't see you. Whereas if you shine a big white light at them, then they can see you, because then you're providing the light that they can see. Rattlesnakes or any kind of pit vipers, the pits are actually infrared detectors. So they can see in the infrared. So any mammal is actually giving off infrared light. And so what happens is that a lot of pit vipers, rattlesnakes, copperheads, water moccasins, they will hunt at night. And that way small prey, small mammals are glowing like little light bulbs for them. And so that's how they hunt. And so that's a different wavelength that you don't see, but it's still out there. Well, it turns out that there's a whole bunch of different wavelengths that are out there, not just visual light. So the visual light makes up really a very tiny part of the total amount of wavelengths that are out there. Ultraviolet light is shorter wavelength than visual. Even shorter and more energetic are X-rays. Even shorter and even more energetic are gamma rays. Longer wavelengths than visual light, that's infrared light, and much longer are radio waves. Now, really short radio waves we often call microwaves. And so they're basically just, all these things are basically just light. And so the difference is how much energy they have and what frequency and wavelength they are. And so this range of light we call the electromagnetic spectrum. So this is all this range of different colors of light. The different electromagnetic spectrum has different energies, different wavelengths, and interacts with matter differently. So you can't just interchange one for the other. Some of it goes through matter easily, some of it is absorbed easily, some has more energy, some has less energy. Ultraviolet light, for example, can damage the DNA in your body. That can cause cancer. Even more energetic are X-rays or gamma rays, they can likewise cause cancer. Infrared light typically just warms things up. Radio waves, even less energy than that. So that's the basic ideas here. Microwaves, all they can do is jiggle molecules. Well, if you jiggle enough water molecules, then that means the water molecules are moving around back and forth, and that's how it heats things up. So that's the different uses of this. There's different ways of making it. Each kind of radiation is electromagnetic radiation is made differently. And so if you detect it coming from space, that tells you some of the physics and what was happening there when it was made.